remember what we were doing last time. We had smiley faces all over in a graph. Let's just do dots now because it's easier. For reasons that I won't explain really well, let's just suppose your features happen to be height in feet. Most of us are between about 4 feet and 7 feet in height, somewhere in there, right? And so we'll put a 4 down here and a 7 up there. And let's suppose the other feature happens to be distance from our beds to this room. And let's do in feet just so we have consistency. And we're, okay, I'm guessing whoever's bed is the closest to this room is probably, I don't know, should we say about 2,047 feet-ish. And I bet you one of us lives, you're at least 5 miles from here. I don't even know how big 5 miles is, but let's say you're 26,948, no, 47 feet from this room. Okay. So we've got somebody over here who's, and what should we predict about us? Let's do something binary because that'll be easy. Gender? It's a terrible one. Sure, let's do it. Okay, you're kind of tallish, and okay, we got some points over here, and there's fewer females in the class, and I don't know. This is a weird, bad analogy. Sorry, but let's suppose you're trying to then predict for a certain point right here, and we're trying to predict who's the most similar to that point, and we're using K and N. Let's suppose it's right here. Okay, now I'm going to rig it a little bit to make my point. Let's pretend there's some data points like this. Maybe I've got it backwards. I don't know. This will be a bad analogy day. Sorry, again, it's Monday. My brain is just not kick-started today. But here's my ultimate point. There's not a lot of variance in attribute vertical, and there's a lot of variance in attribute horizontal, right? And yet, whatever we're trying to predict, well, actually, they're both pretty darn irrelevant to gender. But hey, there is a thing where most boys are a little bit taller than most girls, right? On the other hand, your gender is going to pretty much have nothing to do with how far your bed is from this room, right? I'm trying to say, hey, look, it's very common for your attributes to be scaled differently, and it's going to screw up your predictions. When we do K nearest neighbor, if you just take the attributes for whatever value you get, and if it just happens, what if this were measured in millimeters instead of feet? Then it would be even worse, because then, well, no, actually that's better because this is an irrelevant attribute. Okay, it's starting to come into focus for me. Because this is irrelevant, we'd like there to be a lot of variance because we don't want it to have a lot of meaning. Because this one has low variance, okay, I'm going to take the time to redo it now, and I'm going to actually make my point properly. Sorry. Let's come up with one that has small variance and little meaning. Help me out here now with what's something with tiny numbers and big meaning? Tiny numbers and no meaning.
Age.
Okay, let's go with light years. I'm going to go with light years to U of A, to this room. Okay, how many light years is it from your bed to this room? Pretty not a lot, right? Okay, and then we're also going to measure your height in feet, and we're going to try to predict your gender, and we'll do blue as boys and pink as girls because it's traditional. Okay, so I'm just going to remove the numbers here because they're all going to be 0.00000000000 something, and we're all going to be right around like here ish, And suppose we're now trying to predict that point. What do we get when we measure the k nearest neighbors? Well, clearly, because this point is most similar to those 2 points, assuming we're doing 2nn, this person must be male, blue, because, why? Because they're the same number of light years in distance to this room. Okay, and yet we completely ignored the height and feet factor because we did. And yet, sadly, that height and feet, let's suppose it were more like that, could have made a huge difference because you can actually predict gender by height with some degree of failure. Now, if we had scaled this, instead of measuring light years to this room, we had measured micrometers to the micrometers to this room, what would that actually do? Well, it would take all of these points and scoot them way over here, and take all of these points and scoot them over here. Take these points and it would scoot them way over here. And you see that when we scale, this was not very good scaling. I should have just used the scale feature of my paint program. But all of a sudden we see that if we do the 2 nearest neighbors now, hey, look, who are the 2 nearest neighbors? And it turns out all along this point was female. If only we had measured millimeters, micrometers, to is micrometers, because U looks like a mu, which is the symbol for micro. So if we had measured the distance in micrometers, then we predict this one's female. If we measured the distance in light years, we predict that person's male. Do you see that k and n depends very heavily on the units and on the features, and it's just kind of screwed up by those things. So in general, let's suppose you don't know what's going on and you'd really like to build a supervised learning algorithm that is just going to do the right thing. How do you do it? Yeah, the real answer to my question is you can't. You have to have some meta information about the world in order to do a good job. But probably the best thing we can do is assume that all features contribute equally, right? If we assume that height and distance of your bed to this room both have about equal say in your gender, which is a pretty bad assumption. But if we do, at least we're doing better than arbitrarily letting whichever one happens to have the biggest numbers or the smallest numbers totally carry the weight. So a very common thing to do in KNN is to normalize all your distances before doing KNN. Like that. Yeah, there are actually a whole lot of things that can be done, and we need to talk about that too. So you all know the equation for distance, right? It's the square root of the sum of a minus b squared, where a and b are the elements in the thing you're trying to measure the distance over. Okay, how do you measure the distance between two vectors that are, say, n-dimensional? It's the same thing. Do you take the nth root or the square root? Still the square root. And yet, even though there are n terms under this square root, you still only take the square root, right? Did you know that? Well, that's the case. And why?
What's the definition of it?
Because if you do the Pythagorean theorem and do a bunch of geometry and math, eventually you come out to that. It's just the way it is. It's always the square root, no matter how high your dimensionality is, deal with it. Okay. That's called Euclidean distance. Mahalanobis distance differs from Euclidean distance by one term. See that sigma in the bottom of it? What does sigma represent? Standard deviation. Okay, so if you always divide by standard deviation, what have we done? We've essentially normalized the feature, right? Okay, so using Mahalanobis distance is exactly equivalent to take your data, divide all the features by the standard deviation, and then measure Euclidean distance. The nice thing about using Mahalanobis distance is you don't have to screw up your data. You can just use a different distance metric, and now it's kind of implicitly normalized. And now you can make KNN predictions without having the whole problem of arbitrary features. Of course, you still have the problem of those features have arbitrary relevance to the problem. So there you go. Be aware of that problem. What would you do to beat that? Suppose Instead of using Mahalanobis distance, you want to do something that's more intelligent. What's something you could do? Yeah, okay. So figure out how correlated the labels are to the thing you're trying to predict. I would first scale out all the variance of all the features. Then I would figure out how correlated they are, and then I would scale them up based on, or no, down. Scale them down based on their correlation. So scale them by the inverse of the correlation. So the more correlated they are, the less variance there is, and thus the more influence they'll have on who are the neighbors. That's kind of what you're getting at. Okay. Slightly, because there are nonlinearities in k-nearest neighbor, and you're using linear regression to measure correlation, let me propose a slightly better approach. Let's just take this, but we'll treat each sigma I as a variable to optimize. Excuse me, parameter to optimize. So we'll just do this, and we'll just try various sigma i's until we maximize our predictive accuracy on the training set. There you go. Optimize those values, and now you've got the best possible learner, right? There's a problem with that. Turns out optimizing those values is a big pain. Why might that be a big pain? Yeah, optimization is known to be an NP-hard problem. It's hard to do, but there are various techniques, so you can plug in optimization and do it. Yeah. Yeah, that's what I'm suggesting, is using variance is an okay thing to do. Using true variance basically scales away the arbitrariness from the features, but we also don't know how related those features are to the thing we're trying to predict. And so there's really two concepts here, and deviation is really only one of them. So scaling out the deviation is a good first step, then optimizing would be an even better thing to do. Mahalanobis doesn't suggest that you optimize it. That's my own contribution right now. Okay, does everybody know how to measure deviation? You find the mean, you take the average distance to the mean, call it deviation. You're right. Square it, call it variance, then take the square root and then call it deviation. What I just said is actually something else. They're not strictly equal. I gave you the wrong equation. Okay, and there's some words about it if you want to read about it, and then you can get some more specific details on how to implement Mahalanobis distance. And I say that because, yeah, I'm expecting you to implement Mahalanobis distance for this assignment. I am not asking you to optimize the scale of the features. I'm just saying, let's call this good enough. Why? Because, well, KNN's a really quick and dirty and easy supervised learning algorithm to implement, and Mahalanobis distance is kind of the basic. You have to at least do that to get reasonable results. Okay. There are a lot of other distance equations. So, where is this? Oh, do you guys know about Voronoi diagrams? If you do a one nearest neighbor and you plot this space, so here's an image we're looking at. In this case, I'm assuming we have 1, 2, 3, 4, 5, 6 data points, and the colored regions are the label that would be predicted by a one nearest neighbor model. If you use a one nearest neighbor model to predict some data, it creates what's known as a Voronoi diagram. I don't even know if I'm saying that name correctly. Voronoi? Voroni, whatever. Okay. Well, the point is, the line dividing any two points is exactly halfway between the 2 points and is always orthogonal to the line that would have connected them. And it's just kind of elegant and looks cool, and for some reason we like to make Voronoi diagrams. But in reality, you get better accuracy when you use larger values for n.